All right. Hello. You're welcome to today's chemistry class, and we'll be talking about gas laws. Yes. Now, this video is actually a continuation of the previous video we had on calculations on gas laws. And as I mentioned in the previous video, I actually stated that we cannot finish the entirety of we cannot finish the entirety of the calculations in that particular video. That this will be the continuation, and we'll have a part two. Now, let's do a recap. What we did in the previous video was calculations on Charles' law, Bohr's law, and general gas equation. That is the combination of both. And we spoke about STP and all the rest. But in this particular video, we will not talk about Charles, Bohr's, and general gas equation because we have already covered that. So in case you need help as regards calculations on that, you can actually um, go to my channel and search for it. It has that's the first one, calculations on gas laws. Now this particular one is still going to be calculations on gas laws, but it's going to be part two. Now this one here we'll be talking about Graham's law of diffusion. We'll be talking about calculations relating with it. We'll be talking about Dalton's law of partial pressure, the calculations. We'll be talking about Gay Lussac's law of combination of gases. Yes, we'll be talking about majorly on these three. And at the end of this class, you would have the ability to carry out calculations on gas laws. And we will also talk about the ideal gas equation. So we'll be talking about four different things on this particular video. So at the end of this class, the aim is for you to have the ability and capacity to carry out calculations on any of these topics, any of this topics related or calculations related with it. Now let's hit the ground running. Let's start with the first one, which is Graham's law of diffusion. So, Graham's law of diffusion states that the rate of diffusion of a gas is inversely proportional to the square root of its density. The rate of diffusion of a gas is inversely proportional to the square root of its density. So mathematically, if you are to represent this statement, this will be written as R, which is regarded as the rate of diffusion, inversely proportional to the square root of its density. So this is how it is represented. R is inversely proportional to the square root of its density. Now, when you have this written like this, so if it happens to be a case of multiple gases, so you have, and maybe you will represent the first gas as R1 and the second one as R2. You will have it as R1 over R2 is inversely proportional. So you would have it written as this D2 D1. So what does this mean? R1 being inversely proportional to the square root of D1 and R2 being inversely proportional to the square root of D2. So as you can see, it is not R1 equals to square root of D1. It is R1 equals to the square root of D2, R2 equals to the square root of D1. So that is how it is indicated. Now, one more thing we must have in mind is the ability for us to know that there's what we call vapor density. Now, when you are given the vapor density of a gas, vapor density, which is abbreviated as VD, vapor density multiplied by 2 is actually relative molecular mass. Vapor density multiplied by 2 is the relative molecular mass of that particular gas. So this formula can also be written as R1 over R2 equals to root RMM of 2 over root RMM of 1. So you can work with any of these formulas and you would actually arrive at your answer. Is either you work with this or you work with this. R1 equals to RMM of 2 over RMM of 1, the root of it, and this is the rate of diffusion of the other gas. Now, One more thing we must also talk about is how do we calculate rate. Now, rate itself can be calculated. Rate itself can be calculated as volume of gas over time taken, for diffusion. Volume of gas over time taken for diffusion. This is how we calculate rate of diffusion itself. This is how the calculation of rate of diffusion is given. And the unit of rate of diffusion is given as centimeter cube per second. Centimeter cube per second, meaning that if your time is given as minutes, it should be converted to seconds, except the question demands that it should be in minutes, but it should always be in centimeter per second. Now we've given this analysis, it is time to carry out our calculations. So let's go. Now, if you have a look at this question, it says if 100 centimeter cube of oxygen, which is represented as O2, pass through a porous plug in 50 seconds, what is the time taken for the same volume of hydrogen to pass through the same porous plug? What is the time taken for the same volume of hydrogen to pass through the same porous plug? Now, the first thing you would have to write out is the parameters. I keep saying it. If you are to carry out any calculation, the best you can do is to carry out, first of all, write out parameters. It gives you a clearer perspective and you know what parameter is missing and the kind of formula to work with. So, first of all, let's write it out. We have the volume of oxygen is given as volume of oxygen is given as 100 centimeter cube. Now it passes through a porous plug in 50 seconds, so that means the time taken for diffusion is actually 50 seconds. Okay. Now they said what time is taken for the same volume. So that means if it is the same volume, that means we are talking about volume of hydrogen gas is still going to be 100 centimeter cube. But now we do not know the time taken, so the time becomes unknown. So what else are we going to look into in this particular question here is what we call the relative molecular mass. Now, it was not actually given in this question, but now this is how I have to state it. In case we don't know, H, which is hydrogen gas, hydrogen atom is given as 1, and O is represented as 16. The molar mass of oxygen is given as 16. Now you have this. So what about the relative molecular mass of hydrogen gas? So what is the RMM of hydrogen gas? What's the molar mass of hydrogen gas? You have hydrogen gas represented at H2 will be given as 1 times 2, which is what? 2. So H2 is actually given, the molar mass of hydrogen is 2, hydrogen gas is 2. And we have oxygen, which is O2, which is given as 16 times 2, and that gives you 32. So we would say that the RMM of H2 is 2, and RMM of O2 is 32. This is what they represent. Now we can impute. Then one more thing. We have to look at the rate of diffusion of oxygen, because we are given that the volume of oxygen is 100 centimeter cube and the time taken was 30 seconds. So remember that the rate of diffusion of oxygen is actually going to be given as the volume, which is what? 100 over the time, which is 50, because that is the formula for rate of diffusion. Volume of a gas over time taken. So this is going to give you 2. The answer here is 2. Now we have this for oxygen. So our R, the rate of diffusion for oxygen, is given as 2. But now we have to carry out further calculations, because what was actually requested was the time taken for hydrogen. So you can impute this formula. R Now the R here have to be for O2, that's RO2 over RH2 equals to root RMM, the inverse of this now, of H2 over root RMM of what? Of O2. This is the formula we need to use to actually obtain our time taking. Now, the question is, how are we going to find it? The first thing you're going to do is you use this formula to get the rate of diffusion, first of all, of hydrogen gas. Then when you have the rate of diffusion of hydrogen gas, you then use it to find the time taken. Now, stay with me. Let's do it. Now, I want us to look at this. What was our rate of diffusion of oxygen gas? It is actually given as 2. So we have our rate of diffusion for oxygen is 2, but we don't know the rate of hydrogen gas, so we represent it as RH2 equals to, now the square root. What is the square root of hydrogen, relative molecular mass of hydrogen gas is given as 2. We found it here as 2. Then the next one over the square root of oxygen gas, which we had as 32 here. So we have it as 32. Now, this can also be written, I want you to understand that this statement can also be written as 2 over RH2, that is the rate of diffusion of hydrogen gas, equals to, now, hope you know that this can still be written as 2 over 32. This equation here, root 2 over root 32, is still given as root 2 over 32 here. It can still be written all in one. Now you have represented it in this form. Now, this can also be written as 2 over RH2 equals to, now 2 in 32, if you should divide this or simplify this to the smallest term, 2 here will be 1 and 2 in 32 here will be 16. So this can also be written as 1 over 16. And if this is given as 1 over 16, again, this can still be written as 2 over RH2 equals to, now root 1 is still going to be 1. So you have this as 1. And root 16 is going to give you 4. Now you have it as 4. The next thing we do is what? Cross multiply. And when you cross multiply, you have 4 times 2 equals to RH2 times 1. And 4 times 2 is going to give you 8. And you have 8 is equals to RH2. Now what we've succeeded in doing here is getting our rate of diffusion of hydrogen gas. Now you've gotten your rate of diffusion. So now we have this, then we can now find the time taken for hydrogen gas. Because remember, I have to clean this. Now remember that we are looking for time taken for 50 centimeter cube of hydrogen gas. So we are going to have 8 is equals, no, sorry, actually 100 centimeter cube, sorry. So it's 100 centimeter cube divided by the time. So we will cross multiply and you have C is equals to 100 over 8, which will give you 12.5 seconds. That is how to carry out calculations on rate of diffusion of a gas. Now let's go to the next one. Now, if you look at this question, you have, if hydrogen and a gas with a molecular mass of 128 are at the same temperature and pressure, by what factor will hydrogen diffuse faster, given that your H is equals to 1? Now, the formula we have to work with here has to be our R1 over R2 equals to root RMM of 2 over root RMM of 1. Now let's try to make this make sense.
Remember that our R1 means the rate of diffusion of the first gas, rate of diffusion of the second gas, relative molecular mass of this gas, and relative molecular mass of this gas here. So they are in inverse. They are working in inverse form. Now, they said if hydrogen gas, so that means we are going to represent hydrogen gas. We are going to represent hydrogen gas as RH2, and that of the unknown gas, we'll call it Rx, okay, is equal to the root of RMM of X, because we said the inverse. Now, they told us that the molecular mass of that particular gas, which is unknown, is 128. So you have this represented as 128 over, now it has to be the inverse of the RMM of hydrogen gas, the molar mass of hydrogen gas. And hydrogen gas is represented as 1. Hydrogen itself is represented as 1, but hydrogen gas is represented as H2. So that means if you are to represent hydrogen gas, you're going to have it as 1 times 2. And if you have it as 1 times 2, that means you have this as 2. So they said, by what factor will hydrogen gas diffuse faster? So that means you're going to have this as RH2 over Rx equals to, now this can also be written as 128 divided by 2, and this is also written as root 64, because 128 divided by 2 is actually 64. So you have RH2 over Rx will be given as, root 64 is actually given as 8. So that means by what factor will hydrogen gas diffuse faster than this gas that has the relative molecular mass as 128? The answer is 8. That's actually how to answer questions on Graham's law of diffusion. Now let's have a look at this question. A gas X diffuses twice as fast as gas Y. Now, if the relative molecular mass of X is 32, calculate the relative molecular mass of Y. Now, let's interpret this question. According to this, they said the gas X diffuses twice. So that means if you are to have our formula Rx over Ry, now where R stands for what? Rate of diffusion. So this is rate of diffusion of X, rate of diffusion of Y, equals to the formula you're working with is Graham's law of diffusion. You have it equals to the square root of RMM, because they are going to be in inverse form. So it's going to be the RMM of Y over the inverse of the RMM of X. This is the formula you're working with, because of Graham's law of diffusion says that the rate of diffusion, right? Rate of diffusion of a gas is inversely proportional. It's inversely proportional to the square root of the density of a gas, which is and the density of a gas multiplied by 2 is the relative molecular mass. So you can have this formula here. So when you have this like this, you can now impute it in this formula. So it says a gas X diffuses twice as fast as gas Y. So this statement can be interpreted as 2 over 1. A gas X diffuses twice as that of Y. So it is written as 2 over 1. That is what has been represented here. So Rx over Ry is written as 2 over 1. Now, equal to, now they said if the relative molecular mass of X is 32. So that means our relative molecular mass of X, which is this here, is represented as 32. So you have this as root 32, but we do not know the relative molecular mass of Y. So we represent this as root RMM Y. So what's the next thing we do here? We can actually square both sides. Now, if you square both sides, Now, why are we squaring both sides? To eliminate this root. Now, when you eliminate this root by squaring both sides, so now let's square both sides. If you square both sides, square of 2 is 4, and square of 1 is still 1, because 1 square is still 1, but 2 square is 4. Then when you have this, now the square would actually neutralize this. It will actually, yes, neutralize it by eliminating the square root. So you're going to have RMM of y over 32, because now they are standing on their own, not by the power of this anymore. When you have this, then what's the next thing we do? You cross multiply, and you have 32 times 4 equals to the RMM of y. And 32 times 4 would give you 128. That is the RMM, which is the relative molecular mass of y. So the answer is 128. So this is literally how to, carry out calculations on Graham's law of diffusion. Okay, let's talk about Dalton's law of partial pressure. And it states that if there is a mixture of gases that do not combine, that the pressure, the total pressure exerted by the gases are a sum of the individual partial pressures of those gases. So what this statement is actually analyzing is that if you have different gases, as maybe gas A, gas B, gas C, and they all exert a pressure of maybe 2.5 atmosphere, for example. Now, if they exert this, this is actually a sum of the individual pressures at which they exert together. So this is a sum of what they combine together, because they have what we call individual partial pressures. They have what we call partial pressures. Now, how do we calculate partial pressure? Now, partial pressure can be calculated using two methods. Number one, you can use the number of mole of the gas over total number of mole multiplied by total pressure. Now, this is how you calculate partial pressure. This is how you calculate partial pressure. Another way you can actually calculate partial pressure is volume of gas over the total volume of gas multiplied by the total pressure. That is still how you calculate partial pressure. But need I say this? In case you are given your parameters in masses, please do not say mass of the gas over total mass of the gas. No, you first of all, you convert it to number of moles, then you can use it to carry out your calculations. That is how we carry out calculations on partial pressure. So now we have this. Let us carry out some calculations on it. Let's go. Now let's have a look at this. A gaseous mixture of 80 grams of oxygen and 56 grams of nitrogen has a total pressure of 1.8 atmosphere. Now calculate the partial pressure of oxygen. Now, if, as I said earlier, if you want to carry out calculations on partial pressure, the way to carry out calculations on partial pressure is actually using the formula number of moles of that particular gas over the total number of moles multiplied by the total pressure. That is how you get the partial pressure of that particular gas, because the partial pressure is the particular pressure that the gas exerts in the combination of gases or in the mixture of gases where it does not react. Now, if you are to carry out this calculation, the first thing we should do here is convert our masses to number of moles. Convert your masses to number of moles. Now, if you have this, you have, remember, formula for number of moles. The formula for number of moles is equals to mass over molar mass. Mass over molar mass. And with this stated, let us first of all find the number of moles of the two gases. So for oxygen, now oxygen gas is represented as O2. Nitrogen gas is represented as O2. So for oxygen gas, we have the molar mass first, and the molar mass here is given the molar mass of oxygen is going to be 16 times 2, which is 32, and the molar mass of nitrogen is going to be 14 times 2, which is 28. Now, in case you're wondering how, our O here is given as 16 and our N here is given as 14. So O2, that means I multiply my 16 times 2, which gives me 32, and my 14, N is 14, so my 14 times 2 is 28. So now I have my molar mass. I will now have number of moles is equals to mass over molar mass. So my number of moles for oxygen, our oxygen is 80 grams, so our mass is 80 for oxygen. So my O2 will be 80 divided by the molar mass, which is 32, and the answer will give me 2.5 moles. And now let's go to my N2. My N2 will give me the mass, which is given as 56. Yes, 56 grams of nitrogen. So you have 56 divided by 28, which gives you 2. So we have 2 moles of nitrogen and 2.5 moles of oxygen. So now the formula we are to use to get our partial pressure of oxygen is number of moles of oxygen over total number of moles times total pressure. Now, when you have this formula, you can now get your answer. So remember, they said calculate the partial pressure of oxygen. So now, what is the number of moles of oxygen here? We have it as 2.5. But what is the total number of moles of the gas? Remember, total number of moles of gases. What is the total number of moles of the gas? We have 2.5 moles and we have 2 moles. So the total here is 2.5 plus 2, which is what? 2.5 over 4.5. Now, when you have this, then you multiply it by the total pressure. Now, what is the total pressure here? The total pressure here is 1.8 atmosphere. So you have it as 1.8. Now, when you carry out this multiplication, what you're going to be having is 1 atmosphere. The result you're going to have here is 1 atmosphere. So the partial pressure for oxygen in this particular case is actually 1 atmosphere. So that is the partial pressure for oxygen. That's how to carry out calculation on Dalton's law of partial pressure. Now, let us look at this question. It's still a question on Dalton's law of partial pressure. So let's look at this question again. We are going to have this question analyzed and we'll carry out calculations on it. Now it says, a mixture contains 20 centimeter cube of hydrogen, 35 centimeter cube of oxygen, 15 centimeter cube of carbon monoxide, and 10 centimeter cube of nitrogen at STP, which stands for standard temperature and pressure. Now it says that if the total pressure they exert is 400 millimeter mercury, calculates the partial pressure of hydrogen. Now, how do you carry out calculations like this? There are 2 ways you can carry out the calculations. The first one is number of moles of that particular gas you are looking for the partial pressure over the total number of moles multiplied by the total pressure that they exert. I repeat, number of moles of the particular gas you're looking for, the partial pressure, the gas you're looking for, over the total number of moles of the total gases here, multiplied by the pressure that is exerted, or the volume of the gas over the total volume of the gas of the entire gases here, multiplied by the partial pressure. Now, in this particular case, of the 2 formulas that I just stated, the one that would accurately fit in this question is the volume, the one that involves volume, because the parameters we are presented with here are volume of gases. So, first things first is to look for what they are asking for. They said calculate the partial pressure of hydrogen gas. So, the volume of hydrogen gas here is actually the volume of hydrogen gas. The volume of hydrogen gas here is given as what? They said a mixture contains 20 centimeter cube of hydrogen gas. So that means the volume of hydrogen gas here is 20 centimeter cube. Now the next question we should look at is, what is the total volume here? So we have firstly 20 centimeter cube of hydrogen plus 35 centimeter cube of oxygen plus another one is 15 centimeter cube of carbon monoxide. So it is 15 centimeter cube of CO plus 10 centimeter cube of nitrogen. So in total we have 20 plus 35 plus 15 plus 10. And what is the total volume here? The total volume you're having here is 80 centimeter cube. 80 centimeter cube. Now we can find our partial pressure. Because how can we find our partial pressure? We will have volume of hydrogen gas over total volume multiplied by total pressure. This is the formula to calculate partial pressure. Now, volume of hydrogen gas in this particular question is 20. So you represent it as 20 over, what is the total volume of the gases here? The total volume of gas here is given as 80. So you multiply it by the total pressure, which is given as 400. Now, when you carry out this calculation, 20 in 80 is same as 1 over 4. And 1 over 4 multiplied by 400 will give you 100. So the answer to this is 100 millimeter mercury. This is as easy as it is when you want to carry out calculations on Dalton's law of partial pressure. Now let's move to the next one, and which is ideal gas law. The ideal gas law. Let's talk about it. Now, when you want to work with the ideal gas equation, you have the formula. It is represented as PV is equals to nRT. Now, let us give the meanings of this parameter. P stands for pressure in atmosphere. The unit of pressure in this particular case is in atmosphere. Now, you have this as your volume in dm cube. Please, we have to pay strict acknowledgement of these things. Their units in dm cube. Your n here stands for your number of moles. Your r here stands for the ideal gas constant. It is a constant. It is an ideal gas. It stands for ideal gas constant, and it is presented as 0.082. 0.082. Yes, 0.082. Atmosphere. Then you have atmosphere. Then you also have dm cube per mole. Then you have Kelvin. This is the constant. Then you have your temperature here, and your temperature is in, this is your T. Your T stands for temperature in Kelvin. This stands for your temperature in Kelvin. And T here stands for your temperature in Kelvin. It stands for your temperature in Kelvin. So the recap is P stands for pressure in atmosphere, V volume in dm cube. Your N is not for represents the number of moles. Your R stands for the ideal gas constant, which is 0.082 atm dm cube per mole per Kelvin. And we also have your temperature, which is in Kelvin, and your N is for number of moles. This is the formula you work with when you want to carry out the ideal gas constant. So now let's start. And let's carry out a calculation on it, so you know how to carry out calculations when it involves the ideal gas constant. Let's write. Now let's look at this question. A sample of gas exerts a pressure of 4.1 atmosphere when confined in 2.93 dm cube container at 20 degrees Celsius. What is the number of moles in the sample? So the first thing you're going to do, as far as any calculation is concerned, is write out the parameters. Now, if you have to write out the parameter, the first thing says the sample of gas exerts a pressure. That means our pressure, which is our P, is represented as 4.1 atmosphere. The next one, they said it was confined in 2.93 dm cube. So that means this unit here already tells you that dm cube is a unit for volume. So that means our V is 2.93 dm cube. What else are we looking for? The next thing here, the next parameter given here was 20 degrees Celsius. So that means our T is 20 degrees Celsius. But as far as gas laws are concerned, you cannot carry out calculations with degrees Celsius. It has to be converted to Kelvin. So you have to add 273. So 20 plus 273 gives you 293 Kelvin. Now, that means our temperature is 293 Kelvin. Then the next thing is, what is the number of moles? So what we are looking for in this case is our number of moles, given that our R is 0.082 dm cube atmosphere per Kelvin per mole. So what is the accurate formula to work with when all those parameters are given? And the formula to work with here is the ideal gas law, the formula. So you have PV is equals to nRT. PV is equals to nRT. And you have our, now we've written this, we can now start enlisting them. Our P here is 4.1 multiplied by our V, which is given as 2.93, equal to our N is what we're looking for, it because our N stands for number of moles. Our N in this case stands for number of moles, so we don't know what it is. But what about our R? Our R is given as 0.082. So it's going to be 0.082 times our temperature is given as what? 293, and you have it as 293. Now you have this. We have to collect our like terms and make our N the subject of formula. So you have this written as 4.1 times 2.93 divided by 0.082 times 293 equals to N. And when you have this, the entirety of this here would give you 0.5. So that means our number of moles here is actually 0.5. So you have it as 0.5 mole. 0.5 mole. That is how to carry out your calculations as far as ideal gas law is concerned.
Now let's have a look at this question. What volume of oxygen is required to burn completely 30 centimeter cube of hydrogen at STP? Now, given the equation 2H2 plus O2 giving rise to 2H2O. Now this is 2 moles of hydrogen gas reacting with 1 mole of oxygen gas, giving rise to 2 moles of steam, which is water, but steam. Now, looking at this, first things first is look at the way they combined. We are seeing this as 2, 1, 2. Because the approach you're meant to apply here is what we call the the Gay Lussac's law of gas combination. So, because it says that when gases combine, they do so in what? They do so in simple ratios. They do so in simple ratios and even to the volume of the product of those gases. Now, looking at this, the only way you can navigate through this question is by observing them through the volume of gases, the combinations of their number of moles. Now, looking at this, it says that 30 centimeter cube. So that means this here is 30 centimeter cube. 30 centimeter cube of hydrogen gas. Now, what is the volume of oxygen gas required to burn this? So this becomes unknown. So if you take this here, the ratio at which these things combine are in 2:1. So that means if it took 2 moles to react with 1 mole, this is also going to have the volume as 30 centimeter cube reacting with X. So cross multiply, and you have 2x is equals to 30, and x is equals to 30 divided by 2, which makes it 15 centimeter cube, which is actually ratio 1 of 30. So anytime gases combine, they actually combine in the ratios, in simple ratios at which they combine in their normal chemical formulas. So this is how to carry out the calculations as regards Gay Lussac's law. Now we're going to do one more calculation, and we call it a wrap. Now let's have a look at this question. What volume of H2, which is hydrogen gas, would be left over when 300 centimeter cube of O2 and 100 centimeter cube of H2, which is hydrogen gas, this is oxygen gas, was reacted? O2 is oxygen gas, H2 is hydrogen gas, was reacted. Now, given this equation, 2H2 plus O2 plus 2H2O. Now, they said what volume of hydrogen gas will be left. So now this is how we will attempt this question. Now, how do we attempt the question? We will attempt it this way. Look at the volume, the ratio at which they combine. They combine in 2 ratio 1, giving rise to 2. So that means if we have this, you'll be having something like the combination available here. Now look at, they said would be left over when 300 centimeter cube of oxygen. So what is actually available to react with hydrogen is 300 centimeter cube. And if you have 300 centimeter cube available, so that means if they are to combine in this ratio of 2 ratio 1, what is actually meant to combine with oxygen here will be 600 centimeter cube. That would bring forth 600 centimeter cube of H2O. So if the question is what volume of H2 would be left over, it means that of the available 1000 centimeter cube of hydrogen that was available here, only 600 would react. So that means you have 600 centimeter cube of H2 reacted with 300 centimeter cube of O2. Hence, the question is what volume is left over? So what actually remains here of the H2 in terms of volume will be 1000 centimeter cube, which is the total here, minus what was reacted, which is 600 centimeter cube, and the answer will give you 400 centimeter cube of hydrogen gas. Now that is how to attempt the question. Now, this is it. We have carried out calculations from Graham's law of diffusion to Dalton's law of partial pressure to ideal gas laws to even Gay Lussac's law. Now, all these things are the wrap-up of gas laws. These are the total wrap-up of the gas laws, equations, and all the rest. So as far as gas laws is concerned, calculations on gas laws have been covered in the course of this video. Now remember, this video has a part 1, and the part 1 covered Charles' law, Boyle's law, and general gas law. But this particular one here spoke about 4 others, which is Gay Lussac's, Dalton's, and the rest. Now this is it. I know that you have been enlightened one way or the other, and this is me appealing that if you've been enlightened, you can please share this video to students that require this. You can also give it a like to support the channel, and also subscribe, because this channel is designed to give educative content to make sure that any place of difficulty that we experience, especially in science related subjects, that we cover that. So this is a video that has been designed for such too. So please encourage the channel by liking and subscribing and sharing also. Thank you very much, and see you in my next video, where we'll be also generating more enlightening topics. Thank you very much, and see you. Bye bye.